Okay, I think it's time. Hello everyone, welcome to join Space Observation and Sustainability course today. Today's topic is surface deformation and sea level rise. And the speaker is Professor Kuo-Hsin. He is from the Center for Space and Remote Sensing Research, National Central University. And his research interest is satellite altimetry, satellite geodesy, remote sensing for health-related applications, and multispectral analysis. Okay, Professor Tseng, please.
Okay, thank you for the introduction. Because my wireless internet is probably not very connection is probably not very good. So if my sounds and the streaming becomes very choppy, please let me know. Then I can stop and repeat or just rewind somewhere. So let me first share my screen. Now this is the cover page. So today we have about 2 hours, but I will have a short break in the middle and probably ends in 1:30, 1:50 or so. So I will not use the entire 2 hours. So you can see my title and the topic of the course today will be the sea level rise and the surface deformation. So as you may probably heard about this buzzword since some 10 years ago about the sea level rise, the climate change, global warming, all this buzzword, it becomes very hot topics in remote sensing and the satellite measurement community. So because it's a phenomenon that can, I would not say only, but can be well measured and synoptically viewed from space by satellite measurement, especially the satellite altimetry technology. So that would be a very typical application of satellite measurement. And also nowadays, we are very interested in measuring surface deformation as well, because a lot of these mega cities are suffering from land subsidence due to this urban planning and also this groundwater overpumping, so leads to the compaction of aquifer and so on. So we can also use satellite, for example, using this interferometric synthetic actuator to detect the surface vertical motion. So today I'm gonna combine together. In the end, I will talk about the relative sea level rise. So it's a phenomenon that's when there is a sea level rise, and especially along the shoreline and coastal area, when the land goes down, the subsidence co-located happen, then we will have even worse sea level rise in some coastal areas. So I will show some case, for example, the projection in Taiwan. So that will be today's coverage. My name is Stephen Kuo-Hsin from National Central University. I work in Center for Space and Remote Sensing Research, and also affiliated with Institute of Hydrological and Oceanic Science, and also Department of Civil Engineering. So if you are in Central University, probably you have already taken my courses. So thanks for the TSU, the invitation of this course. So first, I'm gonna introduce the background. So as you can see, there are two plots. One is the sea level rise record from the tide gauge, in the tide gauge era. So you can see that since some 150 years ago, there are tide gauges that keep measuring the level change of sea surface. So except for this diurnal tidal variation, like lunar tide, solar tide, etc., to smooth out all this high frequency signal, we can see a moving average of, for example, annual mean and the 5-year mean of observed sea level. So in the history, we can see that the sea level gradually rise, for example, in this about 100 years, it rises about 8 centimeters. So, which means that the sea level rise rate is very low. So it's like a 0.08 centimeter per year. So it's less than 1 millimeter. It's very gradual, very smooth. However, because the tide gauge only measures like a very scattered coast area, and it's very difficult to maintain the tide gauge. So by the standard, actually, we need to check up this tide level. You know, in the old time, they have this tapping. They use a sort of ruler, like tapping on the coastline, on the dike, or near the harbor, and so on. They need to check up the sea level 6 minutes, or some minutes, or an hour. Every hour, they need to put all these records. So it's very difficult to maintain the very long, continuous, and also very high quality data. So nowadays we have satellites. So satellite altimetry is to measure surface height, sea surface height from space. We use the Earth observation satellite, which is flying the low Earth orbit. We can construct a very long temporal time series, the temporal record of sea level. So you can see that nowadays the sea level rise is at a rate of a couple millimeters per year. So it depends on which agency who post-process the data, but the most common number we see is between 3 to 4 millimeters per year. So you can see the fluctuation includes some interannual signal like El Nino, La Nina. So we can also see some global pattern from this sea level rise time series. But this is a background. I want to show this as a first page because sea level is actually rising. So no matter tide gauge or satellite did see this this rising pattern happens, and especially we call that accelerated rate. The rate becomes faster and faster. So that's why we are we treat this problem seriously, and we want to know how bad it is and how what places, which part of coastline, which shore, which sectors of coastline is more like prone to floods and also coastal hazards in the future. So let me start from some backgrounds of satellite measurement. Probably you have heard about these terms. As I know, I'm the 10th weeks or so. So you have taken already several courses talking about the satellite measurement. So probably some terminology is already in your mind, like the orbital elements, like the payloads. And the satellite, we have a lot of sensors. So for example, to measure the sea surface, we use active sensor. We use microwave sensor, but probably in the past few weeks, you learned about to monitor the surface reflectance, the radiance of whatever atmosphere and so on. They use mostly the passive mode sensor. So today we're gonna use active sensor to measure the length, the distance between satellite and the surface. So either use the radar or laser. And you are familiar with this term, atmospheric window. So it's a very specific spectral window that allows the electromagnetic wave to travel between space and the surface of Earth without serious attenuation of the strength and also the phase and so on. So that's the microwave wavelengths. And also, you are probably familiar with the single band multispectral and hyperspectral terminology. So when we talk about what the capability of the satellite can measure just one frequency, couple frequency, or hundreds of frequencies. For example, hyperspectral is to take images covering from probably visible light to far infrared with some 200 channels. So it's a kind of spec of the satellite. So I think the point is that we need to choose the target and the applications. Then we pick up the right tool and select the correct satellite data and products to use. And once we got the data, we need to do some check first. So the quality assessment and the control, QA, QC, and also the calibration and validation. This CalVal, we always call that validation and the verification. So in some agencies, we call that the VMV. So verification and validation. It's very important when we collect the data from space. We need some in situ data, the ground truth to calibrate the parameters, to calibrate all these algorithms, to make sure that what we measured in space is in accordance with what we measured on the ground. So that would be a good data to use. So I think in the past few weeks, because I also watched the videos, many of lectures talking about the GIS, how to merge different data products together. So in some softwares, and to discuss what is the causality of a phenomenon and so on. So we can see the weighting of which parameters is more important in some solid studies. So that's the processing of data. And finally, the applications. Actually, the application is actually the first. So to me, when we identify a field of application, then we select, we pick the right tool and the right product and to calibrate that. So applications is the for end user. However, it's a very important to know what's your application first before you collect data and learn how to process it. So as you know, satellite can apply to a variety of fields. So like in today's class, we will talk about how to measure the ocean surface height and how to measure the land motion. So, and also how to calibrate the INSAR data by using GPS. So sometimes it's a cross-disciplinary study, not just only one particular field. Okay, so you're also familiar with this wavelength spectrum. It's very important in satellite measurement because once you identify which parameters you want to collect, when you want to observe some phenomena on surface or in the atmosphere or in the ionosphere, then you need to know what is the interactions between this electromagnetic wave and the particles in the air. So normally we do observe the surface of the Earth. For example, we want to see what is the vegetated area, what is the landslide, what is the developed area, to make some classification. We use mostly visible to infrared bands because it can check the surface reflectance the best, and you can use some index, you can use some algorithms to classify, to categorize what kind of land use and the land types. So that's a very common for the EOS, Earth Observation Satellite. And for the atmospheric study, the typical spectrum is in the infrared, from near infrared to far infrared. Basically, we can see what is the structure of clouds, its water droplets, and also crystal crystallized water in the air, and so on, because the particle is bigger, so this will have stronger interaction with longer wavelength. And today we're gonna focus more on the microwave and the radar spectral range. So these are the name for those radar signal. So it's simply like when we call that the shorter wavelength is blue, a little bit longer is red in the visible light spectrum. We give it a name in the microwave or radar signal. The shortest in this radar altimetry domain is most commonly seen as Ka band. And Ku band is also very popular in satellite altimetry. And X band and the C band is more commonly seen in INSAR, the synthetic aperture radar. And the L band is for navigation, like the satellite, like GPS, GLONASS, Galileo, and so on. So the wavelength is mainly between 1 centimeter to 20 centimeters. So that's a very common radar spectral range. So as you can see, it's for within or like near the edge of the atmospheric window. So you can imagine that because the wavelength is long enough, so when the satellite try to measure the range between the antenna on board the satellite and also on the ground, so it's basically weather free. So no matter it's like a thunderstorms or clear sky or whatever, small particles in the air would not affect the transmission of the signal significantly. So only if we use a very short K band, then during when the troposphere has higher like activity, like circulations or more droplets, more water vapors, then it will slightly affect the K band, make some fraction and the delay of the transmission. But most of the time, the microwave can go through in and out the atmosphere. The longer wavelength will be affected by ionosphere. So ionosphere will have some effect applied to L band and the longer one. So when we use GPS, we need dual frequency, we need triple frequency, try to cancel out the ionospheric effect. And the longer one will be the HF, the high frequency, and so on. So you can see that most of satellites utilize spectrum between, I would say, ultraviolets. This is for like ozone study. So all the way up to navigation in L band. So that would be a very common spectral range for remote sensing. So again, today we're gonna mostly use a couple centimeter wavelength to measure the distance. Okay. Oh, I forgot to. Let me just show up everything here. So today I'm gonna cover a list of topics. I'm gonna start with orbital elements, because when we talk about satellite, we need to know this Kepler's element. Then will be in the same frequency. When we talk about the inclination, about the revisit period, about what is altitude of the satellite, then you know that better. Then I'm gonna continue with radar and the laser altimetry to measure surface height. So the surface basically could be different layers. Could be the canopy top, could be the ground surface, and also could be the bathymetry when we use the laser altimetry. And when we can locate it where how high the sea surface, then we can keep continuing measure it to make a time series of the sea level. When we want to talk about the relative sea level height, we also need to know the vertical motion of the land. So we need some other tools. For example, GRACE mission is a gravimetric mission. It gives us an idea which land is actually uplifting and which land is probably like sinking and so on. So it gives us some information about the land, over land as well. Because laser, the altimetry is basically more difficult to measure the motion over land because land has stronger reflection. So basically, it's very difficult to identify or have the same geolocation because the geopointing is another issue. It's very difficult to get the same location, keep measuring it for a long time. So we need other tools to measure the motion of the land. So gravimetry is one of the tools to see a very big area, the regional change of the land. And to check up the details of land motion, we can use INSAR. So INSAR, for example, the Sentinel-1 INSAR mission can give us, I need to delete this GRACE mission here. So the INSAR from Sentinel-1 mission can give us an idea which area has a stronger sinking rate and so on. So we can alert or put some alarm for that area that during some storms and also some storm surge and high tide, then you need to probably you can simulate which area is more prone to flood. And we need some GPS calibration for the INSAR result as well. Then the last would be the relative sea level rise. Probably I have a short pause here. If you have any questions or if you cannot hear me well, you can type or so on. If I hear the type message, then I'll go out and check. Okay, so let me continue. So the satellite motion is very the orbital dynamics. When we described the satellite motion, we use a so-called Keplerian elements or Kepler's element. So basically, there are 6 elements. So when you understand this terminology, you can communicate with other remote sensing people what is the spec of the satellite and what is the purpose of the mission. So for example, as you can see, the first line here between the geocenter and also this is called the perigee. So this is red one is the orbital plane or the outline of the orbit. So you can see that it's evolving, revolving around the geocenter. So you can imagine that this blue plane is the equator plane. So equator plane is the projection of this equator, then it becomes this blue plane. And in this Cartesian coordinate, the x is the so-called vernal equinox. So it's basically a celestial coordinate system. So you can imagine it's a coordinate fixed in space and with the center of the geocenter. So it's fixed in space, x pointing to vernal equinox, the intersection between the ecliptic and also the elliptic and also the equator plane. And z is the Earth rotation pole, and y is the right-hand rule, the third axis. So basically, this is a fixed frame in space, and the satellite keep revolving around the Earth. So basically, you can imagine the Earth is a little bit like moving around the sun in the solar system. But however, most of the time, this Cartesian coordinate system and this orbit plane, it basically fixed in. If you stay thousands light years away, then you will treat this plane as a fixed plane. So let me restart this replay this animation. So you can see that the first element would be the semi-major axis. It's basically describe how high the satellite is. So the low Earth orbiter, when we measure the surface, is basically below 1,000, mostly below 1,000 kilometer above the mean sea level. So here the semi-major axis comes from the geocenter. So basically, if the orbital height, the orbital altitude is 1,000 kilometers, then you need to plus 6,300 something more. So this number is around 7,000 kilometers for low Earth orbiter. And the next is the eccentricity. Eccentricity is to describe how flat this orbit is. So basically to describe the flattening of the ellipse, this orbit ellipse. So for most Earth observation satellite, the eccentricity is very low. It's nearly zero. So which means it's a near circular orbital plane. So when we design a near circular orbital plane, the good thing is that the moving speed and also the distance from satellite to surface is almost the same all the time. Otherwise, it will be moved away, and close to Earth will be a more elliptical motion. And the next one, the right ascension of the ascending node, is talk about what is the orientation of this orbital plane relative to x-axis, relative to the vernal equinox. I think we can pass this. And the next one is the orbital inclination. Inclination is this right. So it's the angle between the equator plane and also the orbital plane. So it basically describes how high the latitude the satellite can measure. So if a near polar satellite mission needs to fly over the polar area, then this orbital inclination is nearly 90 degrees. So if we have like a meteorological satellite, we just want to measure the cyclones, the tropical cyclones and so on, then probably we will design a satellite that with a very low inclination. So it's just flying around the equator all the time. It doesn't need to bother flying over the polar area. So that's the orbital inclination. And the argument of perigee, this is the perigee. If we treat this as an ellipse, this is the focus. Then the closest point to the focus will be the perigee. And the true anomaly will be where the satellite is at a certain moment. So basically, with this 6 Kepler's element, we can describe where the satellite is and what is the mean motion of the satellite. We can sort of predict where it's gonna fly in the next couple hours or so. And also we can use that to predict what is the revisit period and so on. So I think some of them are more important in today's class. One is the semi-major axis. This is to describe how high the satellite is. And also the orbital inclination. That's what is the angle difference between the equator and orbital plane, whether it's 90 degree, for example, 98 degree is commonly seen for some synchronous orbit, or 55 is for GPS, and so on. Okay, so this is a review of orbital elements. Now we are entering the first phase is the satellite altimetry. So altimetry is the sensor itself is called altimeter. So ALTI is to measure the height. Meter is to measure. So to measure the height on board the satellite, we can date back to 1970. So since the Skylab, they use a Ku band scalerometer and also the radar altimeter. But at that moment, actually the vertical accuracy is not good. It can measure the distance, but the accuracy is just sub-kilometer level. So basically, it's not as good as today's very high-end sensor. But it's a start. It's a very important pioneer in the satellite altimetry history. So it's about 50 years ago already, right? So Skylab, the first one, and also the GeoCSat, GeoSat, and so on. You can see that even though there are some gaps in between, but however, all these agencies, they collaborate with each other and try to make a seamless time series to bridge all the missions time series. So basically, the better scenario is that there are a lot of overlapped area between overlapped time between missions. So like NASA and also ESA, they put a lot of effort on how to connect all this time series without gaps. So you can see that. I think the most well-known mission in the history is probably the TOPEX Poseidon. It's a very famous mission in satellite altimetry. And following that, we have GeoSat follow-on, and also EnVisat. EnVisat is one of very famous mission that has multiple applications. So it also measures ocean colors. It also measures the atmosphere and also measures the sea level. So it's a multifunctional satellite on board one satellite. It's like a Sentinel-6 and a Sentinel-3 at this moment. Since 2002, NASA launched a laser altimeter called ISAT. So it used the green and the near-infrared band laser to measure. It basically try to measure the ice and also glacier surface height, but it also play very well over the open ocean. So it's also offer ocean product about the sea level. So you can see this green is the laser altimeter. So today we have IC2. And so this yellow gold time series is the so-called post-limited radar. So it's a very common altimeter radar that it has a symmetric dome shape of radar coverage, the footprint. So it basically can smooth out the ocean width and so on. And since 2010, the CryoSat-2 is a new SAR altimeter. So basically, it's used a synthetic aperture radar technique. So basically, use the coherence of the signal. So we can try to enhance the resolution of the footprint. So it performs better in the coastal area. So CryoSat aims to push the measurement limit toward the coastline, because before CryoSat-2, all this post-limited radar, they use a big footprint of radar signal. So you can imagine the coverage of the footprint is about 5 kilometers, 10 kilometers in diameter, like a 5 kilometers in radius. It's a very huge footprint of the radar signal. Try to measure the average surface height over ocean. So basically, over open ocean is operate very well. However, when the ground track near the shoreline, the coverage will be contaminated or polluted by the land, because land is a very strong reflector. So in the last couple decades, we have a very bad measurement over coastal areas, say within 10, 20 kilometers near the shore. So all this current and also these eddies cannot be revealed very well. However, since the SAR altimeter, the CryoSat-2, and today we got Sentinel-3 and the Sentinel-6, they fill the gaps between open ocean and the land. So we have a better sea level measurement and time series near the shoreline within a couple of meters, a kilometer, within a couple of kilometers near the shoreline. And not only NASA and the ESA, so even the Chinese government, they have Haiyang altimeter, and also India, they have Sara Altica, so they use a K-band. So you can see that it's a family of altimeters. So today, Jason 3, IC2, and the Sentinel-6, we are still try to continue the time series by using many satellite altimeters. Okay, so give me a few minutes to talk about the difference between radar and the laser altimeter. So as you can see, this figure I stole from ESA and CNIS. This is what I call the what is so-called the post-limited altimeter. So you can see that when the satellite send out the electromagnetic pulse, the coverage of that, as I said, the diameter is about 10 kilometers. So the 10 kilometer coverage will have a very good performance over the open ocean because it smooths out all these high frequency waves. Because when we want to measure the mean sea level, the sea level over the coverage area, we don't want the waves, especially this when the significant wave height is like very high, then we want to ignore that. So that's how it designed. It is designed to smooth out these waves. So the advantage is that we can have a very smooth sea level measurement all the way along the ground track. However, when the coverage meets the coastline, as I said, in the so-called waveform, this blue is open ocean waveform, and the red one is so-called the coastal waveform. So in the waveform is the energy, reflected energy as a function of time. So you can see that when the signal hit the coastline, there's a huge anomalous reflection from the coastline. Then it leads to misunderstanding or misidentify where the sea level is because it's a very strong reflection. So we try to avoid this kind of waveform. So that's why in the satellite altimetry community, we have a study group called waveform retracking. Try to retract how to decipher this this waveform, how to identify where is the mean sea level is in the so-called waveform. It's a very important study. So that's the advantage and disadvantage of post-limited altimeter. So this post-limited altimeter, as you can see in the mid, you can see it's symmetric. So basically, it's a dome shape of propagation of the signal. So once the signal hit the sea surface, the center of this circular footprint will be the first to touch the sea surface. So as the expand of the signal in time, you can see that later on, the first reflection will be from the center, and later on in the next some nano to microseconds, the signal propagate from center to the edge. Then the satellite keep continuously receive the signal to form this so-called waveform. So the waveform is from left to right. So when it touch the center of the sea surface, the energy start to increase. So at some certain portion, like half of this circle, the half of this big circle, the energy comes to the peak. And once the energy the remaining energy comes from the rings of the near the edge of this circular pattern. Then the reflected energy keep decreasing. So you can see that the waveform means that the energy goes up. The overlapped area between the signal and the sea surface is become widening. So become bigger and bigger. So when it's when only the ring shape remains, then the energy goes down. So how we identify where the mean sea surface is to identify about the mid to the top of this called the leading edge in the waveform. So that's the key point of waveform retracking. So as I said, the now new technology is called the SAR altimetry. SAR altimetry utilizes a delayed Doppler. So delayed Doppler means that when the satellite move in certain direction, the sensor can check up the coherence between the last and the next the measurement. And also they can use the Doppler effect, because when we have signal sending out, this is a long track direction, because the satellite flying very fast, right? 7.5 kilometers per second. So once it moving away, actually the signal bounce back from behind. The frequency of the signal will become lower, right? And the signal comes in the forward, then the frequency will become higher, because there's a relative speed between the bounced signal and the satellite antenna. So the satellite use this Doppler shift can identify which this cross-band zones of the reflection. So basically, it can increase the resolution in these bands along the track by using the Doppler shift in the return signal. So as you can see in the last page, the Sentinel-3, Sentinel-6 series and the Cryosat-2, they use this measurement. So we can push the measurement toward the coastline better than the conventional Postlimited radar. And the newest one is the so-called laser altimeter. So laser altimeter one is ISAT, and now we have ISAT-2. It uses the green beam laser. So it's visible green laser. So you can imagine it's sort of like this pointer, like laser pointer. It keeps sending out the signal and to measure the surface like the radar. However, it uses visible green light. And ISAT-2 simultaneously send out 6 beams. So it measures 6 points at any moment. And the good thing is that the footprint becomes very small. The footprint of each green circle is only 10 meters. So in contrast to this 10 kilometers. So it's a very small dot with a very high accuracy, vertical and also horizontal pointing accuracy. The disadvantage of this method is because the footprint becomes smaller, so it will be affected by ocean waves. And also, if you want to study how high the waves is, then it's a very good tool, because it can have a very good profile of the sea surface, even the eddies and also the waves height. But when we want to measure the mean sea surface, take a mean of the sea surface, and we need a lot of post-processing of data. So this is an introduction about the measurement. So this is a repeat of some missions from ESA and the NASA and so on. So take EnVisat as an example. The payload on board EnVisat for altimetry is called the Radar Altimeter 2. So it utilizes Ku band and C band. The dual frequency try to mitigate the ionosphere effect. Okay, so this is a principle or the equation of measurements. So How to get the sea surface height? Basically, we need a very good orbital the orbit. Once we need the orbital height and minus the range. So range is from, as I said, this waveform analysis, or it's basically the timing of the two-way travel time of the signal. Then we can get the distance and apply some corrections. Correction is also very important in altimetry because when we want to measure this centimeter level accuracy, once there's a very strong ionospheric anomaly or very strong troposphere activities, then basically the accuracy will be deteriorated. It's basically worse than 10 centimeter or even up to 20 centimeters without good correction. So we need some good background model of the atmosphere. And also we need to understand tides because there are some periodical signal of the land and also ocean, the ocean tide and also salty earth tide and so on, and pole tide. So we need to remove that, take out this high frequency data, then we get the real sea level, the pure sea level signal. And we also need to consider the sea state, what is the significant wave height, and also the inverted barometer. This is about the air pressure. This when they're high pressure and low pressure, the sea surface will have different kind of pattern and retracting and so on. So basically, once we have good corrections for the range, then we get the surface height. Okay, this is another schematic view of the waveform. As I said, when the signal sent out from the satellite, then there is no signal or in the thermal noise level of this waveform. X is time and Y is power. So once the signal touches the center of the footprint, the energy start to come back. And this is the biggest overlapped area, so the energy goes to the peak. Then the remaining ring area will have smaller area, right? Smaller extent, which means the smaller signal strength. So you can see the power goes down. So to analyze this waveform, we need to decompose it. Actually, this waveform can tell us several stories. For example, what is the significant wave height? Because when the wave height is higher and lower, it will change the skewness and also change the entire shape of the waveform. So basically, we can extract some parameters of ocean state from the waveform itself, not only the sea surface, but other like the roughness. And this is a typical real ocean waveform. It's like this. Okay, so this is a laser altimeter. Earlier we have IC2 20 years ago. Not 20 years ago, some 15, I would say 15 years ago. So it measured the height of different layers. So from the cloud tops, because it's visible light, so it's basically not in the atmospheric window, it will reflect it from the cloud top. So it can measure the cloud top height and also the ice surface height, canopy height, water level, and so on. So basically it has various products. But as you can see, because it will reflect it at different surface, so basically it's not exactly for sea surface measurement. It's basically for various surface height measurement. So this is the so-called the photon counting technology. It's a little bit similar to radar altimeter when we try to find where is the peak timing of energy in a series of received echo. So in laser altimeter, we try to count which timing is the highest number of photons come back to the telescope. So we can count and get the peak of that, calculate the time elapsed and times the speed of light, then we can get the two-way distance and divide by 2, then we get the distance. So the idea is pretty much similar, but we use different kind of proxy. So the good thing here in laser altimeter is that we can get different layers, as I said, because the visible light reflected at different layers from the cloud top and also from the tree top, from the surface. So different kind of canopy structures. What is the how high the tree is? We can sort of analyze from the so-called the point clouds of each IC snapshot. And nowadays we have IC2. So IC2 launched in September, I remember, 2018. So it, as I said, it's utilize 6 green beam laser, 3 strong and 3 weak beam. They have different energy level to sort of separate the penetration level of the laser. It's very phenomenal. It's a phenomenal mission because the sampling interval, because it's a very high frequency laser beam. So basically you can imagine along the track every 70 centimeter. So the unit is correct here, 70 centimeter. It has a point measurement of the elevation. However, the coverage, the footprint is 10 meter. I would emphasize the coverage is 10 meter. However, every 70 centimeter, there is a height measurement. So it's very dense, almost seamlessly. You can get a very perfect profile of the elevation along the ground track. And the inter-track, so between the parallel ground track, is the distance is 3 kilometers. So globally, it's a very dense coverage. And the exact revisit is 3 months. So basically, you can see some seasonalities of the time series, but it's difficult to see within a month or within this season. And the point cloud can be used to derive a lot of product. For example, the right-hand side is what also we have done in our lab. We use the laser altimeter. Let me play this animation. I don't know if you can have a good streaming of this video. But it's just a cartoon to show that when this laser altimeter flying over an island, this is Dongsa Island, southwest of Taiwan. Let me repeat this animation. And you can see these photons, these point clouds. We can measure the sea surface and also the sea bottom, so the bathymetry point clouds, 6 tracks simultaneously. So we can estimate what is the sea level is at along 6 ground track. So when we remove this ocean surface, we can have a very good ocean bottom. This is bathymetry. So in our analysis, the depth to measure the water depth, the accuracy is about, I would say, 1 to 1.5 meter, all the way down to 20 meters, 15 to 20 meters depth. So it's very phenomenal applications for IC2. But today, it's just an example of we can also use laser altimeter to measure sea surface height. So this processing flow is for this one of the beam here. Okay, get the resolution of this picture is not very well, but you can check out the NASA introduction about the IC2 mission. So as I said, it measured 6 ground track simultaneously. So 3 of them are so-called strong beam and 3 of them are weak beams. So very dense, and between the parallel ground track, just 3 kilometers. So basically, it's a very good coverage almost everywhere. So let's get back to this time series. We have time series constructed by the Altimetry missions mentioned earlier. So from 1990s to up to today, I'll say we have very good estimation. So at this moment, if you check this sealevel.nasa.gov, then you can see the current rate estimated is about 3.4 millimeter per year. And keep this in mind: the sea level rise is actually it actually has a pattern. It's not like evenly, uniformly uprise everywhere. This is, we call that eustatic. There is a mean rising rate. However, due to this eddies and the different kind of circulation patterns, for some areas, for example, the Southeast Asia and also in the South China Sea and so on, actually, we are facing a higher rate of sea level trend, I would say. So higher than elsewhere. So this is a global mean. However, when we discussed what is the actual rate in the country, then we need to also consider this global pattern. Nowadays, we have a lot of report talking about the projection all the way up to like next century, 2100 years. So it's about 80 years from now on. This is a projection from IPCC AR4. Today we have, this year we have AR6 now. But actually the projection is pretty much similar, I would say. Because in AR4 study, the projection between the lowest to highest is, the difference is about 1 meter. So you can check up this number in 2100. So in the next century, the sea level change, the worst scenario is called A1F1 in the earlier report. This is used as so-called RCP scenario. It's about 1.4 meters. This is the worst case. They use a lot of fossil fuel and without appropriate constraint, and you know, the world keeps developing, and the population, and also and so on. So the moderate and the lower bound will be some 80 to 40 centimeters. So you can see that in the next 80 years, the projection is about 1 to 1.4 meter. So that's the so-called accelerated sea level trend or accelerated sea level projection. If you check the current IPCC AR6, so NASA made a very good website. It's an interactive panel that you can select which kind of process you want: the total sea level, you want to, we want all the parameters, and when is the projection, and what is the scenario. Today, the IPCC AR6, they use a scenario called SSP. This is a so-called shared socio-economic pathway or so. So again, they use different scenarios, fossil fuels and or moderate or renewable energy and so on. So this is the worst case. You can see that in this area, Taiwan is here, Philippines, Indonesia, and so on. So in the end of this century, the projection is about 1.4 meter compared to today. So you can see that in the last couple of years, the projection is pretty much similar. 1 to 1.5 would be the projection of sea level. So probably I don't need to stop. Do I really need to stop, or I can continue without break in the middle? Do I need a vote, or probably because you're offline, you can just go out, take a break by yourself. So I'm gonna continue, or should I stop?
Well, Stephen, you're the boss, you know.
Oh, okay, okay. You found who have a beverage, take a cigarette, just take your time. Okay, then I will continue. So okay, so when we talk about the term relative sea level rise, it's a relative motion between the sea level and the land. Because in most of the coastal area, the land is sinking and the sea level is rising. So actually the rate is more higher than we can imagine. So for example, it's a case of Bangladesh. So Bangladesh, because of the compaction of the sediment and also the overpumping of the groundwater and so on. So basically, you can see these contours. These contours comes from the GPS measurement. You can see that in the capital Dhaka, they have about 1.2. Sorry, this is in the unit of millimeters, so 1.2 centimeters per year sinking, and near the shore is about 5 millimeters sinking. So actually, the rate of land sinking is usually much higher than the sea level rise. So if you only check the sea level rise rate, probably it's meaningless for you, because you could just imagine that's just a few millimeters per year. And my home, my beach house is like 3 meters above the cliff or above the sea level, so it's pretty safe. However, if you consider also your land motion, probably the number will change. So you can see that if we consider both this land sinking and also the sea level rise, then we can have a projection of what is the inundation area could be in the next 50 to up to 200 years. So of course, it's a scenario that without any control, if the rate is linear, if everything stays the same. But however, we know that we need to keep monitoring everything. Then we know some nonlinear rate of the motion, either land or sea level rise. So basically, you can see that it's a case if we combine the sea level and the land motion altogether, it's a very scary simulation could happen. So we also made some other simulations. For example, near the east coast of Chinese coastline, and also near along the Vietnam and the Cambodia and so on. When we take some GPS measurement, you can compare the land motion rate with the sea level rise rate. If the uprising rate is higher than the sea level rise rate, then you're safe. However, if there is a relative contrast motion, then probably the coastal hazard would be worse than ever. So this is very important to show the importance to know what is the land motion. Either it's tectonics, crustal motion, or it's a subsidence due to the human forcing. So I will introduce another mission called GRACE. It gives us a big picture of the geo change or the land motion of a regional area. So actually, it's decommissioned in 2018, but it's a very successful mission. Give us a picture, the temporal change of the gravity field. It's called the Gravity Recovery and Climate Experiment. So it used a twin satellite design, basically one following another. So by using a very accurate distancing signal in between. There's a it can measure a very subtle change of the orbit, because as we know, this orbit motion is associated with to the mass because of this attraction force. So once the attraction force is different for the first and the second spacecraft, actually the orbit will have a relative change. And also when it repeats, we can compare the orbit with the last test, and so on. So we can have a very good gravity recovery from this mission. It started in 2002, and because it tried to measure the gravity field, it's inversely proportional to the distance. So we need the mission, the satellite, flying at very low orbit. The orbit is only 5 kilometers above the sea level. So you can imagine the semi-major axis is about 6,800 only. So the lower the orbit, actually suffer more from the orbital decay. Decay means that because there are air drags, there are solar radiations that can affect the motion of the orbit. So you can see that the altitude of the semi-major axis is moved lower and lower. So actually in 2015, it only have a very choppy data provided. But as I said, it's a super phenomenal, successful mission in the geodetic field. So basically, it used some spherical harmonics. If you are familiar with that, we use spherical harmonics up to 1,000, 2,000 orders and the degrees to describe the shape of the Earth gravity field. Here is a motion made by Michael Schmitz.
Above the Earth.
Probably I can.
As the front satellite approaches an area of higher gravity, it will be pulled toward the area of higher gravity and speed up. This increases the distance between the two satellites. As the satellites straddle the area of higher gravity, the front satellite will slow down, and the trailing satellite will speed up. As the trailing satellite passes the area of higher gravity, it will slow down, and the lead satellite will not be affected. As the twin satellites move around the Earth, onboard instrumentation measures the distance between them, which is caused by the speeding up and...
Okay. So this is an animation showing they use a K-band signal transmission in between. So it can measure the microns change, very subtle change of the orbit in between. So by using the so-called energy balance and recovery algorithms, that we can recover what is the mass below it. So this is an example of the gravity field. It's the geoid. So it's one of the product that can be derived from Greece product, and I think the product more related to today's topic is the so-called gravity field change. So you can see that the raw measurement contains some noise. This we call the striping noise. So once we have some appropriate filtering of the signal, then we can recover the gravity field change. So this figure tried to point out some phenomenon that you can see that there are some red to pink area and warm area and also some cold area. So the darker blue one means the mass loss. So we have a lot of mass loss area like Greenland, like the Antarctica Peninsula, like Bering Glacier of Alaska, and so on. So you can see that some ice field and the glacier area, they put the negative signal in Grace gravity field change signal. And you can probably also see some positive signal here. So the positive signal here is so-called the isostatic adjustment, or the post-glacial rebound. So this area are the areas when the last glacier age, the last glacier minimum, some 10,000 to 20,000 years ago, they were very thick ice glaciers over these areas. So the thick means like 2 to 3 kilometers thick of ice over this area. So all this big chunk of ice put a lot of pressure to the land. So basically, a couple tens of thousands ago, those lands are pressed by the big chunk of ice. So the land basically, it's just like a ball. When you press it, it will like sink, right? So once you release this force, the land will start to rebound. So the land will have a budge that's just like a bounce back, and all these materials and the mass underneath will get together to fill this mass gap. So you can see the increasing mass of this area. We call that PGR, the post-glacial rebound, or the GIA, geostatic glacial isostatic adjustment. So what is the meaning of that? The meaning is that for those areas, the land is actually rising. So there is no land sinking problem. So they are actually facing the land rising problem. So for example, Sweden and Norway, their beach house is actually rising. So they build a beach house, they try to fish at their harbor. However, a few years later, the sea level is actually a couple centimeters or even meters away from their beach house. So because their land is uplifting. So that's not the case in Taiwan. Taiwan suffers from some land subsidence. It's just an example, but for your country, probably you can utilize the INSAR technology to make a map of the subsidence as well. So in Taiwan, we have a stronger subsidence area near the western floodplain, because some arguments say that it's because of the agricultural practice. They pump out groundwater. So this aquifers, different layer of aquifer, they have compaction activity. So after decades of pumping of water, so it's keep compact, the land keep going down. So you can see that the sinking rate is a couple centimeters per year. So you can imagine that the sea level rise is just probably 2 millimeters per year. But however, the land sinking rate is 10 times higher than that. So we really need to treat this problem seriously. So how to measure that? One tool is called the INSAR, Interferometric Synthetic Aperture Radar. Probably you have heard this mission called Sentinel-1. Well, even though Sentinel-1B is now under some investigation, it's a data break since last December. And actually Sentinel-1A is not so stable at this moment, but it already construct a very successful some 4 or 5 years of time series since their launch. So they use radar signal also in the microwave domain. They use the coherence of the delay Doppler signal, try to measure the very subtle change of the length. And the design of the satellite is has a very high repeat cycle. So for example, every 6 days, there is either descending or ascending track. So combined altogether, it's actually a 2-4-2-4 interval of the measurement. It's very dense in the temporal point of view. And why it's become so successful? The point is that because the orbit maintenance is very good for Sentinel-1. The orbital tube is 50 meters, which means that every repeat cycle, the satellite can be controlled within a very almost an exact repeat. So it's very important for INSAR because we want to cohere or compare to phase between repeat measurement. The orbit needs to be close enough, otherwise it will decorrelate with each other. And also the imaging area is very wide, so it's a very good, very useful mission. I think I'll probably quickly go over this this principle of INSAR measurement. So the INSAR measurement, they use the so-called the signal chirp. So signal chirp is a modulated frequency of the pulse. So basically, the modulation of the frequency, the signal, let the sensor knows when did the sensor send out the signal, or when is the front part comes first, or the behind part comes first. So it can determine that it can enhance the resolution in a certain pulse. This is called a chirp signal. So it try to increase the resolution in the distance measurement. So why we call that INSAR? So INSAR, when why we call that synthetic? So the synthetic means that once we send out the signal, so basically a measurement, an object on the ground, it can be measured several times because the satellite has a very high pulse repetition rate. So you can imagine there is one object on the ground. So when the satellite from left to right along the flight path, actually this object can be measured several times. So once a redundancy happens, once we can measure several times, which means that we can increase the resolution of each grid, the grid size can be enhanced. So by using overlapped signal for a certain area, so it can construct a so-called virtual antenna. So the virtual antenna, it looks like a very big antenna with a big aperture, because unless a big aperture antenna appeared here, that we can measure a very small object. Otherwise, once the satellite flying away with a very small antenna, then we can only detect huge objects. So synthetic means that we try to measure an object several times along the path. So to construct an antenna size of several kilometers long. So that's the beauty of so-called SAR. And because we want to know where the satellite, where the signal reflected. So basically, the SAR satellite has a design of the slant looking. So either right looking or left looking. So the right looking means that we can distinguish the returned signal from the near range to the far range. And by using the so-called delay Doppler, we can detect the returned signal either from behind or from the front of the coverage. So basically, we can increase the resolution of the entire footprint. So this is, as I said, we can basically separate the footprint into different grids. So for each small polygon embraced by this dashed line and this solid line is the resolution of each measurement. So as I said, if this is the flight path, this is so-called the near range. This is the range direction. This is so-called the azimuth or flying direction. So the range resolution can be increased by detecting the time delay of the return signal. So we can know which signal belongs to which part along the range. And by using the Doppler delay, the frequency, when you get a return signal higher than emitted signal, then we can say it comes from the front area. Then if the frequency becomes lower, then it's the back area. So we can separate that into this different kind of equi-Doppler line. So equi-Doppler means that for a certain line or for a certain zone, they have the same Doppler shift of the signal. So we can basically separate a return signal or a return footprint into several small grids. So it's very important because when we measure something, we want to know who is the refractor. So this tells us by what time delay and by what Doppler shift, then it belongs to that object. Okay, so this is again another view of the range and the Doppler shift. Maybe you can also check the NASA and the UNESCO. They have a couple online courses over all those materials. So this is, as I said, the synthesized size of long antenna. It happens by utilizing this overlapped measurement for certain objects. When you measure it that several times, it constructs a very long antenna. Okay, so the SAR, the Sentinel-1 synthetic attribute radar, it gives us the product contains mainly two parameters. One is called the phase, one is called the intensity. The phase is when we measure the distance. So what is the phase of the bound signal when it is of this monostatic radar into this monostatic radar? That's the phase. And also the intensity. Intensity is a measure of the strength of the signal. So for that particular pixel, how strong the reflection is. So we mainly record these two parameters. So by using this tool, we can reveal the surface change by using several post-processing techniques. One very famous is the persistent scatter INSAR, or actually in the very beginning, it's called the permanent scatter INSAR by Freddie. So the PS INSAR, it gives us an idea for certain object. If it's a good reflector, we try to measure that in the time series again and again to see what is the motion of that object. So the persistent means that if in the time series of radar image, the intensity keeps high enough and also the phase keeps stable enough, then we treat that as a good scatter. So it's basically a reference point. For example, some buildings or some infrastructures that with right angle to the satellite, or some corner reflector, if you have heard about this instrumentation, that we intentionally put the corner reflectors in the low reflection area, like in mountains, in the forest. We try to learn what is the motion rate of that lens. So basically, for this scatter, we can, the bounce signal, the phase change, it includes several signals and also errors. So this is an example. The measured phase, it includes the actual deformation. However, there are also some errors. For example, the atmospheric error, the satellite orbital error, and also the topographical effect and so on, and the residual air and the like unwrapping air. Actually, INSAR is a very sophisticated, and also it's need a lot of experience to tune all these parameters if you have tried. So, however, for some events that there are also some software and also open source software that you can use, like stamps, like GMT-SAR, a lot of software you can use. So this is an example showing you the time series of the INSAR measurement. So for the southwestern plain of Taiwan. So you can see that from 2015, this is by Sentinel-1A. So all the way up to 2017, you can see that we can see some gradual change of the land, some green, blue colors. So you can see this color bar here. The warm color means uplift. The blue color means going down, sinking. So you can see that the pattern is like, you can see some areas with clear sinking, but you can also notice some airs or some noise. For example, you may probably curious about why there are some uplifting areas and suddenly it moves down, and why there are some very bad image. Because INSAR is basically, it measures the relative motion between images. So basically, for each pair of INSAR result, if you look closely into it, you will see some negative and positive motion rate. It's very common, very normal, because INSAR itself doesn't know the data of the land. So it cannot detect or exactly know which part is sinking and which part is uplifting. What in the result, what INSAR can tell you is the relative motion to the mean surface. So, of course, if there is a change, then when you take out the mean, half of them is positive, half of them is negative. So this what I call before calibration. It means that the INSAR raw result will give you some weird signals because some uplifting part never exists in this area. However, it will be in the result or in your figure. And also, we notice some atmospheric noise, like ionosphere and also troposphere noise, that we can remove that from the atmospheric model, and we can also try to calibrate that by GPS data. So this is to a showcase that in our lab, we try to remove all those signal and calibrate, or I would say to tie the INSAR result with GPS network. So it actually depends on how dense the GPS network in your country. In Taiwan, such a small island, but we have 400, 500 GPS stations because we have a lot of earthquakes. Just a couple hours ago, we had a magnitude 3 something earthquake. So we have a very dense GPS network continuously measuring the tectonic motion. So so we utilize the GPS measurement. It tells us some scatter point motion of the land. And we try to use that to calibrate the INSAR data to make this free rotational data to attach to the GPS, whatever it's ellipsoidal data or whatever data is. So this is the so-called calibration time series of INSAR result. Now you can see that thanks to the GNSS network of this very small circles, small dot, then the INSAR time series becomes very smooth, very meaningful. So you can see that in this so-called Taoyuan County, not Taoyuan, sorry, Yunlin County, we have stronger subsidence. And the rate is couple centimeter. I would say 5 to 6 centimeters per year. Very strong sinking rate. Especially last year, it's a dry year. So due to the climate, last year we had very strong sinking. So this is a validation. So give you an idea that for an INSAR result, without validation is the blue circle behind this scatter plot. So the air budget could be some centimeters. So after the calibration, it's fit better with we use the so-called the leave one out GPS, independent GPS checkup. So the green dots would be the calibrated scatter plot. So accuracy will be still around 1 centimeter, but it's good enough. So you can see what is the seasonality of the change. So it's also associated with the agricultural practice because we have 2 paddy rice crop season. So you can see that the first crop season, there's no rain because our rain starts from the monsoon season in May and later. So before the monsoon season, actually the farmers, they requires a lot of groundwater. So the sinking is more phenomenal in the first half of the year. So probably in your country, you can also have a test to see if we can see the seasonality of the land motion. It's very interesting to see this pattern. Okay, so you can see that we compare our time series. This green dots is the calibrate green dots with red dots. Red line is a GPS dot, GPS time series. So this seasonal signal is what I said. It's depends on the precipitation and also the agriculture phenology. So you can see that we can identify which area is more prone to floods and also coastal surge and so on. Okay, so near the end, it's very important to combine these two together. So we have a sea level rise rate. So probably you can extract that from NASA's webpage, from the IPCC report. You can get the sea level rise rate, and you can check what is the worst scenario or the moderate scenario near the coastline of your country, and put the number along the coastline and try to simulate what is the relative sea level rise and where is the area that has a higher flood risk. Of course, you need a good DEM though. So the DEM here that actually the part I didn't mention is that we also construct a very good intertidal zone DEM. So because for most of open source DEM like SRTM, DEM or Aster DEM and so on, you won't have a good elevation model along the intertidal zone, which means that near the boundary of the land and over the open ocean, there's a stair. You know, it's very weird, but it happens in all the product. Then actually our lab has constructed the intertidal zone DEM to fill the gap. But however, if you have a good DEM, you can make this simulation as well. Then we can simulate where is the flood risk, what is the flood risk along these townships. So you can see that. So the darker, the red means the height, the water depth. So I would say that's the water depth is thicker. So the darker, the worse. So you can see that for some areas, actually for those areas in Taiwan, it's already turned to become some fishing ponds. So it becomes an aquaculture zone instead of agriculture zone. They try to breed fish and the shrimps and so on all the way along this coastline. So basically they know that already. So over several times of typhoon landfalls and also huge storms, they already know which part is prone to flood. So they have an adaptation of the land use already. But we can still have a simulation that's in the end of this century, probably these areas need to be very careful about the flood. Okay, so this is probably the last figure, but I will show you an interesting figure. So this is actually a Stockholm annual sea level variation. So basically, as I said, grades give us a good idea what is land vertical motion, whether it's uplift or some ice melting, the mass loss. You can see that this is a stone in Stockholm. This is the sea level in 1731. This is 200 years later. Actually, the sea level was here, but now it's even lower than this marker. So this is the sea level fall, actually, in the Baltic Sea area. But however, it's not a typical case. It's a very special case in the global sea level rise pattern. But I would say, when someone asks you if everywhere in the world suffer from the sea level rise, actually it's not. Somewhere on the planet actually has this kind of negative sea level change pattern. Okay, so I think this is today's lecture. The summary is here. We need a multi-decadal record of altimetry data to improve our knowledge about the sea level rise, because tide gauge data is limited. Tide gauge need a lot of money, labor to maintain it, the record, and also the quality of the data. The point of tide gauge is very scattered, extremely scattered compared to satellite measurements. So we cannot rely on the tide gauge, but we need the continuing satellite data to give us the estimation of the rate. And also the coastal vulnerability. Coastal vulnerability is also a buzzword. We want to know what is a coastal hazard, what is the sedimentation, what is the erosion, what is the stone surge height, and so on. So basically, when we talk about this issue, we need to consider the relative change between the land and also the sea level. So that's what we learn from different case studies in the world. And many low-lying deltas in Asia are facing severe land subsidence problems, including Taiwan. I know several mega cities. And in Indonesia, they even move their capital to adapt this land sinking problem. So we need some other tools like a synthetic aperture radar can tell us what is the rate. And it's a very good tool for urban planning and to delineate some geologically sensitive areas to avoid the development of that area and so on. So it put some caution, to put some alert for the government to know the problem. And the last statement is that by integrating multiple sensors, so that's the very common that we need a cross-platform of several sensors. We need the altimeters, we need the INSAR, we need optical sensors that we can solve the problem altogether. So whether the land sinking is due to the land use, and whether the coastal erosion is due to the sea level change and so on, or the current change and so on. So we need to merge different data product altogether to solve some big scientific problem in this field. Okay, I'm gonna stop here. I don't know if there are Q&A session, but I will leave some minutes for you to ask questions. You can type or microphone. Okay, I see in the message window. How important is coherence of images in the quality of INSAR result? Very good question. So the coherence means that when we measure a place at least twice, the coherence means actually the coherence is the correlation of the phase in a certain spatial window, in a certain spatial temporal window. So the coherence means that if you have a certain phase, for example, 0.5 pi or negative 0.6 pi and so on, you have certain phase of this measurement. After a couple of days, when the satellite revisit and measure once again, it gives you another phase. The coherence is very important because if the phase is similar in a certain area, it tells you that the solution is meaningful. Because only you have the very high coherence, it means that you are measuring the same object. If the coherence is low, and you still want to solve that, actually it will give you a very bad answer and very wrong answer. And it will even pollute everything near this area because there is one step called unwrapping in the INSAR measurement. Unwrapping means that when we have a phase change, we try to unwrap the phase, accumulate the phase difference along the pathway to get the displacement change. So that's called unwrapping. If you have a certain pixel or a certain area with very low coherence and you insist to unwrap it, it actually will pollute all the solutions next to it because it is a wrong accumulation of displacement at that area. So basically why the coherence is a very important parameter in INSAR processing algorithm, because we want to maintain or preserve more points. However, there is a certain threshold that you need to trade off. You need to sacrifice some point that with very low confidence, you need to take it out. Otherwise, everything will be messy in your result. So why there is a coherence change? One is because of the lens surface change. The coherence, one is because the distance change between the satellite and the surface. If the surface change is has an anomalous change between one pixel to another, so basically the similarity of the phase in the neighborhood will be different between a pair of images. Actually, another most common reason because of the low coherence, because the surface cover, the land cover change. So for example, you want to measure the height of a canopy layer over the forest, over the paddy rice field. Actually, the last time when the satellite flew, you are measuring the very short vegetation plant. And then the next time when it becomes higher, you are measuring actually another kind of plant. So basically you are not measuring the same thing. So the coherence tells you, please don't use this area. It's give you a hint to avoid which part. Do not try to solve it. So please follow this coherence rule. Don't ignore the coherence, or don't try to make a full coverage of everything and use a very low coherence. Otherwise, there will be a lot of noise and a lot of wrong patches that are very difficult to answer. It becomes very, very disturbing. Okay, so that's the, at this moment, the only question I got. I don't know if you have any questions, you are more than welcome to send me an email or through TSU or whatsoever if you are interested in the topic covered today.
Professor, there is a question.
Yes.
from Lin Chi-Hong. Lin-Chi-Hong, can you ask a question?
Okay, so good afternoon, Professor. So I have two questions for you. So first one is we know this satellite is flying in a very high space orbit. So their error will be very big because the orbit will be changed. And when the radar wave they penetrate through the atmosphere, there will be interference by the air, the different density of the air and the cloud. But just like you say, the sea level, the right side, may be only the several millimeter. So how the satellite to get a correct number? Because this is a stay in a very highest orbit. If only use the average rate, I think this is not very good method to correct this error. So how the satellite to get this very high accuracy is the number. So this is my first question.
Okay. So let me answer your first question first. So you also raised a very good question. So for each point or each sector measurement of altimeters, actually the accuracy, the capability is about just 5 to 10 centimeters. I would say that's the limit of all the airs and also all the models. So as you probably know, the orbit area is about 2-3 centimeters. And also the ionospheric solution that we can probably, there's still some 1 centimeter or 2 centimeter air in the ionosphere corrections. Troposphere has lower problem because the troposphere, it affects only the refraction of the signal. So it's a very low, the air budget is very low, some millimeters remains. So I would say, so to combine all this air budget together, the accuracy of a single pass or a single sector of altimeter measurement is 5 to 10 centimeters. So we need a very long time series to fit the line and to get the rate. So the millimeter, how can we get the millimeter rate? Because the time series is long enough. So basically for each point measurement, if there's some scatter and noise, it won't affect the trend. So that's how we get the trend. But for each point measurement, we will not get the millimeter level accuracy.
Okay, so my second question is, so we know there's many different ocean flow in global wide. So each ocean flow that can be carries a very high numbers the ocean water into the from A point to the B point. So my question is because just like your slide shows, the sea level rise up their rates. This is not the same in the global. Something will be rise up more, something will be rise up little. So it's not because this ocean flow, so they move the ocean water into the different place. So that's also what they call this sea level rise up difference. So this is my second question. Thank you.
Yes. So there is several ocean products in. If you check the sea level from NASA or ESA, there are different terminology or different product. One is called the dynamic topography. So there are mean sea surface. There is the dynamic topography. Dynamic means that if there is a persistent eddy or current, then of course because of the push of the pushing force of the flow will push up some areas to have higher sea level. So for example, this crucial eddy will push all this North Pacific Ocean a little bit higher. So it follows the pattern of those eddies. So that's the reason the global sea level trend pattern will be different, because when the ocean becomes, the mass of ocean becomes more. And also one point I didn't mention is that actually the sea level rise, half of the reason is because of the thermal expansion. So the temperature, the thermal haline parameter of the thermal, the temperature, and also the salinity change of the ocean, it will also cause the change of the sea I would say the ocean pattern, the wave pattern, and also the eddy pattern. So eventually put all this parameter together in the model that we can simulate the rate is actually different from place to place. So we call that the dynamic pattern on top of the mean sea level change.
But in your slides inside, seems like near for Antarctica and the North Poles, the ocean, their sea level rise is more, is higher. So what will be the happen? This part of the ocean water should be colder.
You mean here?
Yeah, in the right side of your slides.
Oh, sorry. This cooler water actually is cooler at this moment, but the global ocean has a thermal expansion. So it doesn't matter what is the exact temperature of today, but the global ocean water becomes warmer and warmer. So it will expand everywhere. And around this Antarctica, there is a circular eddy around this. And sorry, I forgot the exact name, but there is the circular pattern of the of current around the Antarctica. So basically, there is also a dynamic topography of this place. So it's not related to the latitude of the ocean, but it's about the physical pattern of the ocean of the current.
But when that happened, near for equatorial ocean water, this is the hottest. But why their level rise of speed is not red? It's just blue. It's only yellow into the green.
Oh,
equatorial water shows is the most hottest.
This is the pattern. This is the rising red pattern. So if it's warm, let's keep it warm. If it's cooler, let's keep it cooler. However, it's the rising rate is the same everywhere. We try to heat up for 1 degree or 2 degrees. So basically, the difference between this pattern is not the exact temperature of that, but the circulation pattern. It caused the trend difference from place to place.
All right. So thank you, Professor.
Okay, if I didn't clarify clearly, probably you can find some other materials. Any other problems, if you have any? Okay, so let's go back to the quiz.
Okay, thanks for Professor Tseng. Thank you very much. And everyone, please write down your answer word for last 2 questions and use this Google Form. This link I write down in the chat room. Please check it.